My name is Eugene. So in previous videos we discussed my model of reality or my understanding of reality. Um, so in this video I'll discuss how particles behave um, in the framework of that model. Um, so as we know from elementary science, if we have two particles that are similar, they tend to attract towards each other, but as soon as they get close to each other, they bounce off each other. So these particles have this an essential dance with each other, where they come close together, they repel each other, and they come close together. So in nature, right, everything flows in rhythms. So that is reflected in how particles behave, um, where everything has a waveform essentially. Even if we look at light rays, um, science say that particles have a dual nature where they can either be, or light has dual nature where it can either be particles as photons, or it can come in waves. But in the model that I understand, um, it's more like the particles when a light ray travels in space. The light is essentially a series of particles, and in fact, based on my model, we live in a particle-based world. There's no such thing as waves. The wave is just um, a result of the behavior, or is a result of the interactions of these particles. So when these particles, when these light particles travel, and typically they explode. Typically they explode from a light source. They are essentially ejected because of an explosion. The light particles get ejected, and the light particles, it's not a single type of particle. It's typically a whole cluster of different particles, right? And as they traverse through space, they essentially exhibit this dance where they come close to each other, and then they move away from each other, and they come close to each other, move away from each other, come close to each other. So when it travels through space, it travels essentially as a cable through space, where all these particles, they have this dance around each other as they travel through space. So it's more like a helical shape. So when these light particles interact with something that can make them bend, for instance, there's a gravity field, right? And when I say a field or gravity field, it's essentially just a whole bunch of particles that that is clumped together or that moves together. But essentially, it's influenced by something in space. So what happens then is that this cable splits off, right? Or perhaps it splits off, and now this particle that are attracted, they stay together. Others that are not as much attracted splits off in a different direction, right? So typically that could result in different spectrum of light being split off, where maybe your blues go that way and your reds go that way, and so to the observer on this side, the light is no longer a pure light. It could be a reddish light, it could be a bluish light, or it could be whatever combination of light. But essentially that's one behavior of particles. the question is, why do these particles behave in such a way? So, as we discussed in our previous video, right, we have our universal bubble. So we have a universe, and it is rendered by a single subatomic particle. It bounces around, in this resonant cavity, and we observe it by having a instrument that's fine-tuned or tuned to a certain frequency, so that can be observed. And wherever this particle crisscrosses, it produces a particle, or it is represented as a particle. So essentially, the entire universe then is filled with areas where this particle crisscrosses. So that equates to the entire universe is filled with particles. Now, in this room, obviously, we have air, we have magnetic radiation, and who knows what else. But just because we can't see it, it's still there. Even if we go into space, deep space, it is teeming with particles. And that is just based on my model of reality. So what does that mean? So if if the entire universe is filled with particles, so that means there's always a background sea of particles. So and they all have different different types of particles, depending on how many times that virtual particle crisscrosses to produce different shapes and sizes of particles. So if you have a set of similar particles that's floating around in space, right? These particles tend to clump together, right? They tend to clump together because of the pressure exerted by other particles that they are floating in. So because they are different, right, they are essentially not of the same density. If I could use that term just to hopefully give you a better understanding, but they are essentially of a different density. So the particles that are not similar essentially exerts a force on them. So the force is typically in the same direction, so that these particles then tend to clump together, and we observe them essentially as being attracted to each other. In this case, they're not really there's no communication between these particles to make them attract. It's just that other particles pushes them so they can clump together. And when they clump together, and also another reason they clump together is because they take up space. Just based on remember we discussed that this universal has a set of rules, and part of the rules is that there cannot be vacuums. So if you have a medium, right? In this case, well, if you have a medium filled with, you have some sort of medium, right? And you produce an area where there's no medium, right? For instance, let's say it's liquid, right? And somehow you produce a vacuum in the middle of that liquid. What's going to happen is you'll get a implosion where this liquid suddenly rushes into that area to fill that void. But the reason they rush into that void is because of the pressure of the surrounding liquid, right, that pushes them into that void. So that is, one of the other rules. So if you look at this, right, so our media then is the background particles, and where these particles exist, this area represents a vacuum. So essentially these background particles want to fill that vacuum. So as they move to fill this vacuum, they push all these particles together so the vacuum can be filled. So what happens then is when these particles, when these black particles, when they come together, they experience a crowding of particles. So another rule of the reality is that these particles, when two particles approach each other, they cannot merge. They have to push off each other, right? They cannot go through each other. They bounce off each other. So what then happens is when these particles come together, they experience crowding, and then they push off each other because of the crowding. So in that way then, these particles would come together, push off each other, and then the pressure from the surrounding media pushes them back, right? Similarly, you could have, different, other particles of a different type. They would experience, the same dance where they clump together, right? And then they explode away from each other. So that's essentially the main reason why these particles tend to behave in this way, where some of the particles come together, and when they are close to each other, they push away from each other, and most likely because they in a area where there's a sea of other particles that exert pressure on them. That's one way of how these particles move together. Another way is these particles could get attracted to each other. For instance, you have two magnetic particles, or let's say two magnets, right? Those are essential big particles. Now, if we have opposite poles, they tend to come together. Opposite poles attract each other, and then similar poles, right? They push away from each other. So why is that, right? You have no other surrounding media that exert pressure, but yet they exhibit that behavior. So there's a different, different mechanism involved in that. So essentially, if you have, how do magnets work? I guess let's discuss that. So we know in elementary science that if you have a magnet, you have a magnet has a north and a south pole, and I forget which one is the inlet, but let's say the particles come into the north and escape through the south, right? And then they travel around, right? So these particles, they have a definite entry and a definite exit, right? And now if we bring another magnet, let's see. So we bring another magnet, and let's say it's south pole, there's north pole over there. So if particle escape through south, come through north. So what's happening here, the reason why they push off is because you essentially have, let's see, this is a pump, right? And this guy is pumping water out. This guy is pumping water out this way. So the two streams of water meet, right? They push off each other. Similarly, if we make this a north pole, let's say this is north and this is south, north and this is south, right? So now we have the fields reversing. Now we have the stream, the pump going this way. So, and imagine this is in water. Right. So we have a pump that sucks water in through this end, and we have a pump that sucks water in through this end. What happens if you bring those two pumps together, right? It's difficult to push them together because they still push off each other, and the reason is because this inflow, right? This inflow of water particles essentially results that these guys stay away from each other because they have to, go into the inlets. So that's essentially, when I envision a magnets, I envision pumps. So let's take a closer look at, how that works. What is the pumping mechanism? So when you take a piece of iron, right? We know from science that we have atoms in the iron, a sea of atoms, and because it's a metal, in this case iron, they float in a sea of the atoms inside the iron. They're free to move, or more or less free to move, so they can spin. So in the case of iron, then we have the atoms appear to be magnetic, right? So in unmagnetized iron, we have the ions just floating around, and their magnetic fields are random. So when we apply an external magnetic particle flow or magnetic field, we essentially align all these atoms so now they point in the same direction. So we kind of twist the atoms so they're all aligned with the magnetic field. Right. So now this magnetic field, or this external magnetic particle flow, is enhanced because now all these atoms, they are aligned in the same way, and they contribute to the flowing of magnetic particles. Now we have more magnetic particles flowing in and out, right? So we take a closer look at why these atoms have a magnetic field, or have a magnetic pole essentially. It definitely has, if you look at the atom itself, it has an inflow of magnetic particles and an outflow. And the reason why this is so, because the iron atoms essentially has a certain frequency. When these electrons, or when you have these subatomic particle cloud that's around the nucleus of the atom, it has a certain frequency, and at a certain frequency it expels a subatomic particle. In this case, let's say it's a magnetron, which represent a magnetic particle that makes up a magnetic field. So it expels this magnetron, and then as it expels the magnetron, it creates a vacuum. And as we stated before, when there's a vacuum, that vacuum has to be filled. So that particle then is either you have another, perhaps you have another iron atom. So it contributes a particle to this atom that lost the particle, or this particle simply curves around and go back into the atom. So that's essentially what makes iron magnetic, is because its atoms is such that it expels magnetic particles. When it's unmagnetized, it's random, and the magnetic particles that it expels is replenished by other atoms, and the one that it expelled maybe end up in a different atom. So the magnetic particle path within the ion, right, unmagnetized, right, is always flowing within the ion itself. Now, if you magnetize it, right, and there's various ways of magnetizing it, where you shock it by hitting it in an external magnetic field that aligns the atoms, so now they are all aligned in the same way. So when you, let's say when you have an external magnetic field, if it's weak or strong or whatever, right? So what's happening now is that this external magnetic field, as these particles flow through the atoms, and imagine again this as a hose of a strong hose, or a strong flow of water coming through, and we have pumps just floating within this container. They randomly, they have the random flow. So as soon as you shoot all this water through this way, the inlets, right, they start aligning, right? They start aligning to the flow of the water. Okay. So now we have all these pumps focusing in the same direction. So now the flow of water becomes strong, and the sucking in of water also becomes stronger. So that is the same way, the same way how the ion becomes magnetized, is where these atoms get aligned in the same direction as the external magnetic field, right? Now if we somehow, if this magnetic field is strong enough, right, and it's able to permanently move these atoms, or orient these atoms so they all flow in the same direction, you take away that magnetic field, now suddenly the ion becomes magnetized, because all its atoms are pointing in the same direction, right? So when these particles shoot out, creates a vacuum, right? Because we have intakes over here, creates a vacuum on this side, so it has to pull, and these particles typically tries to find the closest magnetic inlet, right? And the closest magnetic inlet would be on this side, so they bend back and come in. Now we also have free magnetic particles floating around as well, and those also get sucked in as well. So essentially that's how a magnet works. Okay, so next video we'll discuss how gravity, my model of how gravity works, based on our previous discussion on the model of reality. Um, it also works in a similar way, as how these magnetic particles interact with each other, and our particles in general interact with each other. All right, so see you next time.